So for this presentation, I will show you some optimizations that you can apply to your code. These are not depending on the compiler, but then I will give you some hints that when you are compiling with the Cray, so some directives that you can use and so on. So it's not specific to any compiler, except that, of course, I will give you some detail of the Cray compiler, but you can do the same thing with other compilers, except on GNU. I guess they don't have the same possibilities sometimes, okay? So essentially, you have your code, and essentially, you think that the compiler will do all the optimization for you. So people, when they are running on x86, like Sandy Bridge or Intel, they really think that anything I'm writing there, since it's really smart CPU, they will try to organize in a way that is, at the end, I will get best performance, right? So this is not completely true. So you are somehow bound to the hardware. So you need to write good code, thinking in terms of the hardware, okay? So then there are people, they really like to think in terms of hardware. I'm not one of this person. But the thing is, you need to trust entirely what the compiler is doing. So you really need to want to see what the compiler is doing and try to solve and help the compiler to get the best performance, best optimization, okay? So in this talk, I will cover essentially 3 kinds of optimizations: loop optimizations, cache optimization, and vectorization, okay? So there are no fixed rules, so it depends on your program, it depends on your application, then you can apply some of them or not, okay? So when I mention the listenings, it is very useful because you can see -r, you can set -m, right? Was the flag I explained before, and you will get the output on the screen saying what it's doing for the loops, if it's applying blocking, vectorization, unrolling, how many times it's doing unrolling, and so on, and blocking, and so on. But there is also another flag, which is D, and this flag, the compiler will dump you 2 files, okay? One file with the name of your file .opt, and another file is CG, and this is a kind of, in case opt is something readable from you, it's how the compiler is taking your file, is changing in a way, and then it's compiling the new version of the code, okay? So for example, the compiler will apply a rolling, okay? In this file, opt, you will see the loop with a rolling, okay? So you can easily understand what the compiler is doing, how it's changing the source code, let's say in this other way, try to improve performance. The other file, CG, is something, it's a kind of meta language. It's something not easy to read. So if you want to play, you can use the Cray compiler in your program, whatever, and you can set -rd. And then you can look at those 2 files. Usually from these 2 files, I see, well, most of the time I use those options to see if the compiler is doing something wrong, okay? But in your case, maybe you are interested to see how to change the code to improve it, okay? Of course, you can trust the compiler, but then if you move to another compiler, maybe you want to use the same optimizations, but maybe the other compiler is not able to apply the same kind of optimization Cray is doing, so maybe you want to see what the Cray is doing, okay? So you can have a new version of the source code with optimizations. So essential hardware concept. This is the schema of the Sandy Bridge pipeline. Oops, sorry. Easy question. Is anybody understanding what is this guy here? All right. So what I am interested is that Sandy Bridge is called auto-order architecture. Okay? There are 6 ports. Each port is able to do simultaneous 4 operations. What does it mean? Suppose you are running your program. In a given part of your program, you're making some operations. Let's say a sum of 2 numbers. Okay? So this operation, you need to load the value of A. Let's say C equal A plus B. You need to load the value of A. You need to load the value of B. So there are 2 loads from memory. And then you need to put the A plus B. Okay, A will be in a register, B will be in a register, A plus B. The new result will be in a new register, C. And then you need to move back the value in memory. Okay? So there are several operations. All these operations can be simultaneous. If you are loading A and you are loading B, you don't need to wait for A. But at the same time, you can load also B. So people, they realize that they can do these operations out of order. Okay? They are just not fixed order, not A and B. You can do also B and A. Doesn't matter. At some point, you need to synchronize because you need to do A plus B, of course. But it doesn't matter. So all those ports can do different operations. for example, these two ports, port 3 and port 4, they do load and store from memory. So you can load at the same time A and B because we have two ports, they can do in parallel the same operation. Okay? This is just to give an idea. The same thing you can do for floating point. You see here, these are the AVX registers. So essentially, you can do multiplication floating point, you can do add floating point, you can do shuffle, Boolean, and so on. Okay? At the end of the day, you need to synchronize. Okay? This is it's not useful, but it's just to keep in mind that if you want to understand what is really doing in the hardware, you need to understand this guy here, and you need to understand that at the same time, you can do 4 instructions per cycle, 4 different instructions per cycle. So for example, at the same time, I can do 2 load, or I can do a load and a store, and I can do also 2 AVX operations. Okay? As well, the new architecture by Intel has 8 ports. Okay? Now, what is interesting is that we can load 2 elements from here. We can store, we have a port just for storing. So if we are doing a lot of load and store, so a lot of reading elements, storing elements, of course, we saturate these 2 ports. So then if I need to do, a lot of these operations, then all the other ports will do nothing, okay? So maybe it will be better to optimize this. Sandy Beach will do for you, no problem. Okay, there is an internal hardware system to optimize for you. What is interesting for us, questions? I mean, it's not trivial to understand, but it's just to give an idea of the hardware complexity. Okay? For example, here all the instructions will be cached. This is the level 1 cache instruction. This is the level 1 data, okay? And so on. So you will read all these elements, and of course, the system is doing prefetching, so it's trying to figure out the next instruction. Then there are things for branch prediction, okay, and so on.
So if you were just doing a rough you only get 2 instructions per cycle, because only 2 ports.
Sure. The other strange thing you can imagine is this. AVX, I will tell you later, is a 256 bits register. So essentially, you can do, since 64-bit is a double, you can do 4 doubles in one cycle, 4 doubles. So suppose I want to do 4 and 4, right? And then I need to read 4 elements, 4 elements, 4 elements. Otherwise, it will not work, right? Unfortunately, what you can read at the maximum is 32-byte load, okay, and 60-byte store. So the problem here is that I can do 4 operations, but I can read just 2 elements. Okay? In Aswell, they introduced in the new system, they introduced also FMA. So the possibility to do 2 operations, 4 elements, you can do products and sum. Fuse, multiply, add, okay? So this is the reason why they add the other 2 ports, because they need more load and more store, because otherwise you will have to do more operations with the same data. It doesn't work, okay? So they add 2 more ports, I guess, for what? For load and store, okay? So there are other 2 ports, 8 ports. Still, you can do still 4 operations per cycle. This is the maximum, because then you need to reorder all these operations, okay? You need to store C, because if you're using C in another operation, you need to store first C, and then you will use another operation. So this is the way how it works internally. GPU doesn't have anything about this. This is why the GPU is so fast to do easy operation, but then it cannot do any out of order, okay? So if you write your program, it's a really bad program, then all this technique by Intel, well, it's not by Intel, all the technique inside the Sandy Bridge, okay, they will try to figure out how to improve the optimization, the code, and so on. Just scheduling the operation in a different way, okay? So you can get good performance. If you move this in order, like a GPU, if you write not the perfect code, there is no way to gain performance, okay? There are a lot of concepts related to branch prediction and so on. GPU doesn't have anything about branch prediction. Sandwich is really good to do branch prediction. So to understand if the operation is true or false, by the way. So what is interesting for us is how we access data, okay? If the data is, okay, we have hundreds of these registers, bytes, we need 1 cycle to access. It's putting less than 1 cycle just because I can access, since I have the AVX registers, so I can access even more data, okay? But when I move from registers, which are inside the CPU, to L1 cache, I need 3 cycles, okay? So if something is not in a register, but it's in level 1, then I need 3 cycles to access. I like to put in this context. If I have 3 gigahertz CPU, 3 cycles means that now my CPU is going to be 1 gigahertz. Okay? 1 gigahertz is old Pentium back like 6 or 4 years ago, I think 10 years ago. But if the data is not available in level 1, so level 1 is 64 kilobytes per each core, you have 32 kilobytes per data and 32 kilobytes per instruction. Sometimes you can have also missing instruction. It's really complex way when you are doing jump in instructions and so on. Starving for instruction is called. Level 2 cache, about 10 cycles. Again, you can make the comparison. So I want to do fast operations, but then I cannot access the data because they are not there. I will show you examples what not in level 1 are level 2. So I need to do more cycles. And level 3 even worse, okay? Level 3 is shared between the cores. So sometimes I want to have optimization in a way that I can reuse my data and so on and so on, okay? Okay, if you're reading from the disk, fine, okay? So I want to reuse my data. So there is this principle of data locality, okay? So I want to reuse my data so that the data are in the registers. I can do a lot of operations. So there is a concept of locality, spatial locality and temporal locality. So I want to use data which are close so that I can stay in the same cache. Or I want to reuse the data over time. Okay? So I need to optimize my program to do this kind of operation. The compiler will not do this kind of optimization for you. Okay? So let's say you do a matrix multiplication. You are writing the matrix multiplication. You have a pattern for data. So the compiler will understand what is the pattern of your program, not for the data, the programming model. So you need to optimize, and I will show you some of this optimization in a way that you can improve those principles. Okay? Now people are making also this comparison in terms of power consumption. So if you move from a register, they have some consumption. If you move for cache 1, a different consumption. So if you like work with iPhone, maybe you are interested to do something like this, mobile and so on. All right, what is the SIM instructions? I just described before. So suppose I do this loop. I have 4 elements, okay? So in an AVX register, I can have 4 elements, right? So I have A and B, okay? It's 256-bit. Now I can do this operation in a single cycle, 4 operations, so single. Of course, I need to load the elements, okay? So I need to have this data. So AVX is this guy. SSC was previous situation with 2 double precision numbers and integers. Now AVX is still not supporting integers values. With Aswell, they introduced AVX2, where they have integers, and they have other operations, gather, scatter, and so on. It's a really complex situation. You can imagine that GPUs, since we will discuss after lunch for GPUs, are vector machines, basically. Okay? So they have very large vectors. Okay? So SIM operations are very important to consider because you can go 4 times faster just making use of SIM. Okay? I mentioned before, in this easy loop, but still, you can apply in different cases. So loop unrolling. Essentially, you have this loop here. Now, since I want to, it will be better just because of prefetching, because of vectorization and so on, to change this loop in this other loop. Now, I'm making chunks of 4. So the block, the unrolling block is 4. I will write explicitly these 4 operations here, right? So then I do jump of 4. Both loops are the same, right? Here is with explicit unrolling, okay? Does that make sense? Anytime if you have questions. Okay? Of course, if this n is no multiple of 4, then I need to take care of this, okay? With this loop, you can gain some optimization. In the old time with the Fortran 77, it was really common. If you go to look in BLAST, for example, you will see code like this. Now, nobody is writing like this because the compiler will do automatically this guy here. In the Cray compiler, if you do -rm, it will say, OK, rolling. How many times is our rolling? Okay? You will see the roll block. So R4, for example, which means like this case. And this loop is faster because it's accessing data faster. Okay? So the good point is that you need to avoid to do a rolling by end. You just need to understand what is a rolling. Trust me, the compiler can do. Actually, when you are doing optimization, it depends also on your hardware. So if you do explicit unrolling, and then you change from a system to another system, maybe you need to change the code, which is not the best thing to do. If you are using the compiler, maybe you are recompiling. So if you are compiling for Sandy Bridge, it's different from Aswell. Easy. You just recompile. You have the specific flags, and they will do a rolling for you, right? So this is just to mention. But sometimes maybe you want to apply a given amount of rolling. Why? Because sometimes, for example, this n, the value here in the loop, is unknown. It's unknown to the compiler. And then maybe you have some idea. So the compiler will apply some heuristics. But if you know what is this n, usually n is 100, okay? Sometimes it can be 4, okay? Who cares? Sometimes it can be 100. So you can apply this kind of directives before the loop. Here, you put on top here. And you can specify which is the level of n. So you can force the compiler, do unrolling, but with this kind of blocking, okay? So usually it's good enough to leave the compiler to do the job. Otherwise, you can specify your values. Strip mining. It's just, in this case, instead of one single loop, we are making 2 loops. And the reason is that you want to do this operation with a given value, this strip length. In this case, it was 1,000. So it's like before, but in this case, we have an internal loop, and we are considering piece of 1,000. So the internal loop, we jump 1,000 and 1,000 and 1,000 chunks of 1,000, okay? So now let's move to a specific case. Is clear? These are the 2 techniques that we can apply for loops to get some kind of optimization. There are really common optimizations. Again, these kind of things the compiler will apply for you. But sometimes we want to play maybe to optimize. If you know that in a piece of code, in a specific loop, the compiler maybe is not able to get performance, and you spend most of time there, maybe you want to really apply this kind of optimizations, okay? So let's take this example. They told me that it's a real example, so I'm just writing what they told me. So I have to multiply A times B. The point is that some values are 0. So I want to skip those values, okay? So some kind of code will be like this, right? So I have first loop, second loop, and I want to do the sum over this multiplication of the elements, okay? But in some cases, this mask can be 0. Some cases can be 1. For 0, I will not do any operation. For 1, I will do the operation. Clear? A times B, sometimes I don't want to just because it's 0, okay? So this mask will be 0, 1. And sometimes, so with 0, no operation. With 1, do operation. And then I do accumulation because I'm making the multiplication. And then I'm storing the value on the result, R, okay? So what we know is that the mask is 50% of the time is set to 1. The other 50%, of course, is set to 0. So this is the trivial code, right? Some kind of other optimization I can apply is just remove the mask. When I have an if inside a loop, this loop, since maybe the mask can be 0 or 1, likely will not apply any kind of optimization, vectorization, okay? This if is called a branch, okay? It's a branch because you are making a choice in 2 cases. So sometimes it's able to predict what is the branch, it will do the right operation, sometimes not. Again, if you run a piece of code like this on the GPU, I don't know what are the performance. It will do the both, right? Both solutions. It will do 0 and 1. And then it will throw out if it's wrong branch, right? Yeah, we'll do both.
But if the condition is true for this thread, when it comes to the else part, it will go through the instructions but not do anything. It's just spinning. So what it means, and then for the threads where the logical value was false, they will spin during the if part.
Yeah, they will just ignore.
Then they will actually do the operation.
So it's not able to do the branch. It will do both operations. And then one of the operations will do nothing, basically.
Yeah, so let's say in this case, all of the threads will do the if instructions and the else instructions. But for only 50% of the time will they actually do work.
Yes, the other 50% is doing
but it means that,
nothing.
If the if and the else have the same number of operations, it will take twice as long to do it.
Yes, yes, yes. So with the CPU, you have some kind of branch prediction. So you can predict before doing the operation if it's true or false. So it will do the correct operation. For the GPU, it's quite unlikely. So both basically.
Well, yes. Well,
so it's twice slower. There are some tricks there, but yeah. So it's twice slower. On the CPU, maybe you don't lose performance. But still, let's remove this. Let's do the operation. Actually, if it's 0, who cares? I mean, it will sum with 0, right? So the final value will not change. So this is the first thing. Don't care about the mask. The second thing is that we will change. You see here, there are 3 loops, right? We will change this order, this order of the loops. So now we are making A, K, and J instead of I, J, and K. We are just changing the order, okay? This is C. You should remember that C is ordering by columns, okay? So you are moving about J, then you change I. Fortran is the other way around, okay? So just keep in mind. So I do this because here now I can use, since I'm moving about J, I can use this guy here, and I can use this guy here. These are consecutive in memory. Does anybody understand this? Okay? So loop better for these two, this and this. Of course, now it's jumping, K is fixed, so who cares? This is fixed over this J loop. So it can do better access to R and B. It can do also vectorization because there is no branch and so on. Back the mask. Okay? Now it's see thing with the mask again. Okay? And then I can do also these kind of things. Okay? So I'm doing now the mask multiplication. So instead to do a branch, I'm doing an operation. Then if the mask is 0, this value will sum 0, right? If it is 1, we'll just save the value. Okay? So instead of have a branch, I'm doing one more operation. People now, they like to say that it's better to do operations instead to do load store from memory because it's consuming more, okay? So I'm just doing instead of a branch operation. The result will not change. Do we agree? Okay. Last thing is to use the libraries. In this case, use SGEM, so the BLAST library. So essentially, I'm doing this operation, submitting the values to the results. So you have already the answer, but of course. So first thing with the mask is 5 seconds. Second thing, straightforward, there is no difference. Actually, it's lower. So x86 Sandy Bridge is able to understand, very smart, is able to understand the branch, is able to predict the branch. So even if we have an if there, it will just understand, and you lose performance. Again, if you do on a GPU, you can expect some penalty. So when you're moving without a branch, you should go faster, essentially. With the CPU, basically are the same. But now you change the loop. The compiler will not do that for you, okay? Pay attention. And you see there is a huge speed up because now we are accessing R and B, remember the example, in a better way. It's also able to do vectorization. Now back the mask. Now in this case, I'm putting the mask. You see the branch here was the case before, and now it's slower because in this case, the mask will destroy vectorization, even if you have branch prediction. Okay, so you lose performance. And then you use gem, and you see this, sorry. Then there is the other case where I'm putting the mask as operation. It's still working well, so better than this. So it's better to avoid branches, making operations, but it's not like this, okay? And then you have the blast. And blast is much, much faster. It's the reason why it's better to use libraries instead to write your own code, okay? So why this guy is faster? Sure.
What if you put the mask in the outer loop, like out of the loop?
The mask depends on I and J.
Yeah. So I and K. I and K. So you combine the loops I and K, like the first, yeah, like
I and K.
You could hold that outside the J.
Here?
That would improve vectorization.
Yes, yes. I think then it's wrong because it should depends on K and J. But because, yes, otherwise it doesn't make any sense.
well, anyway,
You can put outside.
it depends on 2 of them.
Yeah, it depends outside. Yeah.
So that, yes, that might be
Sure.
what does the standard for C say for this? Is that version of the mask multiplier, is that standard compliant?
Yes,
So logicals are set to be 0 and 1, are they?
yes. Yes, so this is 0 and 1. Okay, 0 is false, 1 is whatever. And this will apply mask operations in assembly. Oh, Fortran, yes. Yeah, anyway, that's a good point. I will fix it just to avoid this comment in the future. So the example was not to move the mask, okay? The example was to play around with the loops and so on, not to move the mask. But true that you can do this kind of optimization. So the point is why BLAST is so fast. faster than what we have implemented, okay? Not changing the mask, okay? So the reason is that BLAST is applying cache optimization, not just loop optimization. Can I change the slide? Okay. So Microsoft PowerPoint has stopped working. 1 second, please. And at some point, even Microsoft is stopping to work. Windows entirely. Coming back. Okay, so what they apply is the cache optimization. Okay, so let's take an example. First point is, I showed you before, when you are the Sandy Beach schema, we know that AVX is able to read elements padding, let's say, with a given. So you can read 32 bytes, so it's a given line. So if you're putting elements in a wrong address, it can be the case like this. Okay, so in this case, when it's declaring A, B, and C, they are contiguous. They are putting on the stacks. Okay, and when then I need to read A and read B and read C, since these are consecutive, if I want to have better cache layout, so putting these elements in a better way, I need to put some padding elements. So now I have A, 64, 64, right? Then I put other 16 elements just to have, this is just because I need to have some layout memory, so follow layout memory. Then I have B, then I have other elements, okay? So now these all elements are with this given padding, okay? And when it's trying to access A and B and C, they will be in the right position. So it's better to access memory. So this compile will do for you. So that's, and then nobody is now putting in common. This is very Fortanol style.
Okay, so why have you chosen 16?
This was just an example, because 32-byte cache line. 64-byte cache line, sorry, 64-byte cache line is the load store.
And it's because A and B and C, their dimensions are all 1 to 32.
Yes. So the technique, so it's one solution, but the compiler will do for you. So just declare elements with some padding. This is very common. In Fortran, it's not common, but in C, when you have, for example, some, let's say, objects and so on, usually you put some values up the position of the elements. Let's say you put a char. Char is 1 byte, and this 1 byte, you know, so they will change the address. So put the integers in the right position. We can do the test. With the sides off, you do a structure and you can see the dimension. It will be not 5, but it will be more than, because it's putting padding elements. So the solution, we want to improve cache locality, right? So we can, with this, the technique is cache blocking. So we want to reuse the same data on the cache to do more operations. So with this technique, you need to understand for which level cache you want to optimize. So people, they use to optimize for level 2 usually, because you have enough cache available per core. Okay, it's not shared. Okay, so you can optimize so that you can reuse the data on the level 2. Okay, if you optimize for level 1, depends on your algorithm. For example, you can optimize for level 1. Maybe it will be not easy to do that. Okay, so I will show you some example. So the point is that you need to try, and again, the compiler will not do for you. Okay, this is something that is implemented inside the BLAS libraries. This is the reason why BLAS is so fast when you are writing your code, with respect to your code, right? Because they do cache blocking, essentially. So they try to figure out the pattern on the data, and they try to reuse the data in the cache. So let's take an example. I hope it will not crash anymore. Yes, this is an example. I want to make this stencil operation, so I have 2 loops. I want to make this operation here, right? So I have the first external loop with 8 elements here, J1 to J8. And then I have the other loop, 16 elements, going from here to here. Okay, I'm just assuming, okay, this is not a Sunday bridge, okay? I'm just assuming my cache line is 4 array elements. So I can read in a cache line in one single 4 elements. Doesn't matter if it's float, real, okay? This is just metaprogramming, let's say. Then my cache can have 12 lines of data, okay? So 4 cache line times 12 is the maximum number of elements I can have in the cache, okay? So let's start with the operation, first loop, okay? I start from here. I need, since I need also the neighbors, I need this, and this, okay? I'm starting with J1, I1, okay? And I need also the other 4 elements, okay? I do the next operation, and we'll start. So now I need to read 3 cache lines. You see, 4 elements, 4 elements, 4 elements. I cannot read less than a cache line. Sorry, then a cache line. So to read one element, I need to read the entire cache line. Those 3 cache lines are not in the cache, so I need to read from another level of cache. And remember, from level 1 to level 2 and then to level 3, there is a huge difference in number of cycles. So in the meantime, I'm reading, the CPU will do nothing because he has to read the data, okay? So this is a first iteration. Just to make a simple operation, first iteration, I need to read 3 cache lines. Then I start to move, okay? You see how many lines I'm reading now? It's moving over over I, okay? It's increasing the number of cache lines it has to read. If the data are in the cache, then it will, if there is no space in the cache, it will remove the data from the cache to read the new data. So this is 12 cache lines, 12 lines of cache, which are in the level 1 or whatever their cache. So this is what I have in the cache, okay? For doing the first iteration, I need 15 cache lines read, okay? Because they are not in the cache. Now I move to neighbors. I move to here, so 15 cache lines. I move to here. To do this other operation, I need to read again the neighbors. The neighbors are not in the cache, so I need to read back for the next level of cache. I'm not reusing the data which are in the cache. I need to read again from the next level of cache. So I need to read the other 3 cache lines, 18, and move. At the end, another line, 30, and so on, up to the end, 112, 20, sorry. So for doing this kind of operation, I need to read those number of cache lines. And remember, from one cache to the other cache level, there are at least times lower. And this is an easy example. So how can I improve this? First thing we can do is blocking. And we will do blocking for the inner loop. And we'll do blocking for 4 elements. Now you see 4 elements, 4 elements, 4 elements, 4 elements. Let's see if it works better. You see there the result, actually. So the first iteration will start here. Now we are stopping here and moving in the other direction, okay? You see? At the end, we'll start to read. So you see how this is the cache dimension, and I'm reusing the data inside the cache. I'm going not to the end. I'm just reusing the data in the cache. First iteration, 12. Next iteration, I have 20. Again, this gray part is the cache, okay? Everything you have in the cache. Now I move to the other block. 20 here, 20 here, 20 here, 20 here, 80. Previously was 120. Now it's 80. I read less from the next cache. I'm reusing the same data to do the same operation. Again, you can do now blocking also in the other direction. This is easy case, of course, in reality, maybe you not so trivial cases, but still, it's something that you want to apply. So now, again, I can do the same trick. But now I'm moving from one block to the other. So it will complete this block. It will move to the next block. And again, and again, and again. And it's still reusing data. OK? So at the end, when he's moving to the entire these two blocks, then it's moving to the other. I have 60, an half of the previous case. The compiler will not do any kind of optimization like this. So you are better to use data on the cache. And again, if you are optimizing for level 2, maybe the blocking will be for level 2. Because moving from level 1 to level 2 is 2 times lower, twice lower, but it's nothing there. From level 2 to level 3, there is large differences. Okay? And level 3 is shared. So if you have multiple cores running, the level 3 is shared, they will compete to access to the cache. Okay? So this is how to change the code with kind of blocking. Okay? All right. So the blocking doesn't work. So the first solution is you are doing wrong. Okay? Maybe the block size is too small. So you need to figure out if you can improve these things. Maybe you are optimizing for wrong level of cache and so on. Of course, most of the time the compiler will try to optimize. If you have nested loops, we will try to optimize some of the internal loops. Okay? We'll try to apply some kind of, because the compiler knows how many cache lines you have, so he knows the hardware. So he will try to optimize applying blocking and so on. So maybe there are other effects like prefetching of data. So while you are doing some operation, you try to read the other data in the meantime and so on. Okay? So there are techniques already available on the hardware how to improve this situation. But sometimes loop blocking can give you very large performance. Okay? All right. Of course, we can use also directives. Okay? So this is the original loop. Then, of course, I can apply some kind of directives. For example, in this case, for example, I'm just saying, OK, do loop blocking for j and k. Okay? And then I'm saying what is the size of this blocking. So I can have this kind of, and the compiler will say, OK, wow, I have this loop. I will apply these two directives. I will change the code in such way. So you don't need to directly write your code with the blocking. Okay? You can do this kind of tricks using directives. Okay? So there are other techniques, like we have two different loops. So usually you want to use the data. For example, here we are using A, right? So suppose this loop is very large. You will fill the cache with B and do the operation in A, right? But then you move to the next iteration. Then I want to restart to reuse A. But unfortunately, for the next, for example, A11 is not available anymore in the cache, so I need to fetch again, right? I need to read again from the next cache level. So what maybe is better is to fuse the two operations. So to have fuse, otherwise I can have two loops, two internal loops, but the external loop will be the same. So partial fusing. Okay? Also, in this case, the compiler usually is smart enough to understand that we have two different loops, and they will try. These are trivial cases again, but sometimes maybe you can have other operations in different functions. Maybe you can try to apply this kind of optimization, try to improve the performance. And yes, this is the case, for example, when you essentially you have a function, so you are calling two functions. And in this case, you can have better treatment if you're putting the loop outside of the function, and then inside you call the loop. There you will do inlining of these two functions. So basically, this function will be here, called directory. And essentially, you can imagine this is very important when you're moving to GPU, because in GPU, if you don't have inlining, there is no possibility to do vectorization. If you don't do vectorization, I said vector machine, essentially. So you will not have any kind of performance. And this is also important to keep in mind when you are using Fortran, this kind of operation, these are kind of loops. So it's unlikely that the compiler will apply kind of optimization for these kind of operations. Okay? So maybe you want to write directly in this way.
There's a bug in that slide.
Okay, good. It's
My fault, whoever wrote it should find it. But subroutine sub1, the arguments there should be A and B.
A and B.
Inside it should be A, B, and J.
Ah, yes, right. Yeah, A and B.
Passing different arguments, the trick is that the J has been hauled up into the calling routine.
Yeah, so it's moving J, yes.
That's the only thing. The arguments should be
So it's A and B here, and A, B, and J here.
Yes.
Yeah, okay. So this is an example. So we are doing this 3D decomposition. It's, again, stencil operation. You have these three loops, right? Okay. This is the local grid. So how many elements you have? There are 248. Okay. So we will see how to change this loop, making blocking how we can improve the performance. And depends on block size, we can see how they change the performance, okay? So the first thing to do, let's say we'll apply blocking here, an internal loop, okay? And you see how change the block size from unblocked to the other block size, the performance. Okay, here in this case, we are doing really bad because the unblocked is faster than the others, okay? But now you can change in another way. You can do another different blocking. You see, now I'm changing the block here and here. Previously was only the two internal, okay? And you see now the new performance. You see that with this new blocking, we are doing better than unblocked. Actually, here is the fastest. No, here, right? So you can do this kind of tricks. You can play around these values, okay, to get better performance. Just reducing data, okay, on the cache. This depends, of course, on the cache you have available on the system. But at least level 2 cache is not changing from Sandy Bridge to Aswell to Ivy Bridge. It's fixed, okay? They just extend the level 3 cache. Level 1, it is the same. So if you are optimizing for level 2 with a given block size, usually you can keep this kind of optimization for another system. So vectorization, this is kind of trivial. Okay, so you have this register with 128 bits where you can have 2 doubles or otherwise 4 single. AVX is an extension essentially. So you have twice more bits now. You have what they call line 0, line 1. So you can imagine that AVX is like 2 SSE registers. So you can do this kind of operation, plus minus multiplication, okay? And essentially, you will do twice more operations, so you will get a speed up of factor 2. Unfortunately, the division and square root is not supported by AVX. So I had a situation where I was making in a loop, I was making divisions. I say, okay, well, let's do with SSE something. Then I move it to AVX, I got the same performance. And the reason is that the division was not supported. So even if you're using AVX registers, they say that the latency is twice more. It's just cheating, okay? The latency is twice more, so it's just using 4 operations, but it's twice slower. So at the end of the day, it's like 2 operations. It's like SSE. So the square root are not supported. If you're doing this kind of operation, you should keep in mind that you gain from vectorization from AVX respect to SSE. So Intel is working with AVX2, will come with Aswell, but there is also an extension to 112 bits, which is now it's available what they call Intel Xeon Phi, which is the accelerator, or mic, or whatever you want to call it. This will be available in the next generation, Skylake, something there, in 4 years from now, I think. Okay, so we need to use those registers. So what we can vectorize is only loops. So we have a loop, and we'll apply this kind of vectorization. So essentially, if you are using AVX, and you fill the registers, you can do 4 operations in 1 cycle. So you're going to be, the loop, it is 4 times faster, okay? So usually the vectorization will apply the internal loop, but there are also techniques that will apply also on external loops, right? So essentially, the compiler will try to use vector instructions. So you need to understand if it's really vectorizing and why it's not vectorizing, okay? So sometimes, for example, it's not able to vectorize because we are making some kind of dependencies. I will show you an example. So you need to change the code in a way that the compiler will try to vectorize. Okay, you need to force to vectorize, unless you want to really change the code using intrinsics or funny stuff there. Okay, so essentially you can look in the assembly, okay, and see if it's using vector instruction. If you are a fan of assembly, I can tell you what the instructions. Okay, it's packet instruction for 256 bit. Okay. And of course, you need to take care that I mentioned before. There are just 2 ports for load and store. Actually, 3 stores, 2 loads. So you cannot have, I'm doing 4 operations. So you cannot have, at the end of the day, you will vectorize your loops, but then there is no gain in performance. And the reason is that I need to read data from memory. And it is a limited bandwidth, okay? So, you know, you do a lot of operation, then there is no real way to improve the performance. So let's say this is a case when you have, okay? you use for the next iteration. So this kind of loop cannot be vectorized easily. Okay? There are directives that you can apply, for example, to because the compiler will stay safe, will not try to vectorize. Otherwise, maybe you will get wrong results. Okay? So just to be safe, the compiler will not vectorize. It will tell you, it seems that in this loop, you can try. Any loop, the compiler will tell you, it seems that in this loop, there are dependencies. It seems that between iterations, you are using the same variable. So something wrong is there. Okay? Usually with C, C++, it's really common because you use pointers and it's a mess. Okay, it's a mess. So you need to compile to the compiler that there are no dependencies. There is this wonderful program here, directive, that you can use to avoid this kind to avoid this kind of dependencies. So then the compiler will vectorize. Okay, OpenP4 now is using also SIMD directive to vectorize in any case, even if you get wrong results and so on. Okay? So this other case, for example, you have here making, first you have a loop over I, okay? And then you have another index inside the loop, okay? And then you use this index for your vector, okay? So I is the index of the for loop, for example, and then inside you do another index based on basically on I, on the number of iterations, and then you use this. Maybe in this case, that will not vectorize. So the best thing will be forget about count, and you just put here 2 times I. Okay? So now as index, I'm using again the index from the for loop. And we'll try to vectorize. Okay? Even if you have branch, the compiler will generate what they call masking operations. Okay? Masking operation, it's a vector instructions, and they just avoid some operations, okay? So it will generate a mask and so on. So it will try to vectorize in most of the case. Another thing to keep in mind is that the elements should be consecutive. If I'm making a loop jumping over 10 elements, okay, so I'm reading the first element, then I'm reading element 11, then element 21, and so on. These elements are not consecutive. So the compiler should read from, the system should read from memory, put in the registers. So this kind of operation is called gather. The elements are not consecutive. This is really common in C++ because usually we do with objects. These are structural array of structure. It's something related to the fact they are. So these are stride elements, so jumping of 10. The compiler will do for you, okay? The system will do for you. Sometimes the stride is not constant. So the first element is a position 1, the other element is position 12, the other one is 100. You need to do jumps. There are different load and store. This will destroy any kind of performance, okay? So these two operations, scatter and gather. Gather means read from different positional elements, which are not consecutive. Scatter is the opposite, basically. Store the elements in not consecutive position. This is implemented in AVX. I mean, one of the performance is really, really bad, okay? This is coming from old Cray machines and back in 80s with vector instructions, okay? So essentially, there are several cases where it's not easy to vectorize. So you need to really understand if the compiler is able to vectorize. Maybe he's misunderstanding your code. So there are flags for doing that, okay? And from these flags, you will really see if why the loops are not vectorized. Otherwise, you can look at the assembly. You can have minus capital S flag, and you will see what is going on, okay? So I was to complete with this example, taken from this guy in the front. So this is the example here. If you look, these are legacy, okay, coming from old people. So old fathers. Okay, so this is the example. You see here, I'm making 2 loops. The internal loop is saying, okay, this is a rolling a factor 4. Okay, this is just to say this is a rolling a factor 4. And then it's telling me 2 messages. It's saying, okay, I cannot vectorize here, and I cannot vectorize here. It's just saying that it's doing a rolling. One means that it's the external loop, okay? It doesn't matter this, okay? So why it's not able to vectorize? Why? Because here it's putting this value here, okay? So it's filling this vector, and then it's using the same element here, okay? And you take this time. So how you can improve this? Solution. Okay, if you go to the next slide, you will see the solution. But please, take a few minutes to understand it. OK, the solution is you can make 2 loops. With the external loop, you will just do this operation. Putting in a vector, OK, you will just do this. And then here you use another vector. So I'm not using anymore this guy here coming from here. I'm using a vector now. So I'm just changing x from a scalar, single element, to a vector. Yes, I'm using more memory, because now x is not 1 byte, sorry, 1 element, it's an array of bytes. And then I'm doing vectorization. So here it's trivial, it will do vectorization. And here it's also doing this. Then it will do other operation, it will change the order, all that other stuff. This is the compiler. The new version is faster. Okay? You will use more memory, but then it's able to do vectorization. Usually, one example is, can you vectorize a factorial operation? Do you know that? Factorial. N times n minus 1 times n minus 2, and so on. It's not possible. Okay? So don't think about this. Okay? But this is just an idea how some cases can be easy vectorized, some cases not. And how you can change the code is a trade-off between memory, right? So you can include some vectors, some other elements, just to avoid this. Usually when you have if statements, so you have an if statement, say it's greater than 0, do something, less than 0, do something else. Okay? Trivial. So what the compiler will do, it will first do the switch, put the new elements in new arrays, and then run the new loop, 2 loops now, with new arrays, making just everything greater than 0, everything less than 0. So at the end, we will vectorize. So there are several cases where you can apply these kind of things, okay? Usually the compiler will try to do for you, okay? So there are some kind of initialization. There are also cases, for example, this is really common in C++, again, where you have huge loops. You have a loop with, in the middle, like 1,000 instructions. So to get this loop to vectorize is impossible, because in 1,000 instructions, unless you are doing easy operation, usually you will get a function. And this function will not be inlined, and you will remove vectorization, okay? So how you can vectorize this? Suppose this inline function is at the end of your loop, and all the rest can be inlined, okay? So what I will do is to split the loop. I will do a loop for 999 instructions. This loop will be vectorized, and then I will reuse the data for the last instruction. I mean, it doesn't mean that I need to have the extraction at the end, okay? It can be in the middle. So I can split the loops in several loops so that I can get vectorization at a given portion. Then I can do another loop which is not vectorizable because this is a linear function. Why I say C++? Because in C++ they use virtual functions. And by definition, virtual function cannot be inlined, okay? So it's really common that you will get a virtual function somewhere and the loop will not vectorize. So you can split your loop to get vectorization in some portions of the loop, okay? This is something cases. Okay. So these are the conclusion, essentially. So tomorrow we will see how we can look at the performance of your code using Cray path. So you can do profiling analysis. We can use hardware counters to understand how many AVX instructions I'm doing, how many vector instructions I'm doing. So there is a way inside the CPU with the call PMU, Performance Monitoring Unit, which is a way to understand how many operations I'm doing. So in this way, we can easily understand if our code can be improved or not, okay? Actually, at the end of the day, you can say, I'm using my CPU for 10% of total performance, for example. There are ways to say that. So, okay, you can trust the compiler, but sometimes maybe you want to understand what the compiler is doing. So there are ways to improve what the compiler can do. So you need to avoid branches inside loops. You need to avoid the function which can not inline it. And then you need to understand feedback from the compiler and so on. And then vectorization is crucial. So just to give you an idea, so why Cray compiler is so good to inline? Because then you will get vectorization. But there is also another reason. Since we use OpenACC, and I said, for GPU, you need to be vector, okay? Because otherwise, you will not get performance. So it's so aggressive to do inlining just because then they have OpenACC, so the possibility to move to the GPU, where you are forced to use inlining, okay, to get vectorization. That's it. Questions? So just to give an idea, I was working at CERN in, again, Atlas spend like the guy is doing. You are working Atlas, you said. You? Yes. Yes. So I work in Atlas. They have 2 million lines of code, C++. They have this large loop, external loop. Yes. So it's a really common situation. At some point, they said it's impossible to do vectorization. And it was true, because in the old time, Pentium was supposed to run at 8 gigahertz. Okay, so you say, okay, it's everything for free, right? So and now what they say in Intel, the lunch is over. So you need to take care of, and vectors are the easy things to add to CPUs to get performance. So moving from Ivy Bridge to Aswell, they just have twice more flops because they included FMA. Then still we have 256 bits. Then you will move to the next generation where you extend twice the length of the registers, so factor 2. But if you don't use these vectors, it's like my old boss said. It's like to say that I have a car with 4 seats, okay, and I have 4 persons, so we can run the same car 4 persons. Instead to do that, we use 4 cars, which is not convenient, right? So this is the reason. So I'm really interested to use vectorization and so on. And that's really important for GPUs. So if you have code you want to play with the vectorization, the first thing I will do is run with the Cray compiler, get the feedback, and then we will see if we can improve it, how we can improve it, and so on. Last time we got a guy who was trying to do that. And we spent like 1 day to do this kind of optimization. And then at the end, it was not changing anything. The performance was the same. So at the end, I said, well, let's try to see what is the memory bandwidth of your application. It was saturating the bandwidth. So there was, even in doing the vectorization, there was no reason to improve it, the performance, because it was not possible to read more data than what he needs. So this kind of things is something that you can play. And tomorrow we will see with the Cray part how to see where we can improve the code and so on. Question?